The rational numbers form an ordered field, and between any two of them lie infinitely many more rationals. That abundance still leaves gaps. Density supplies points between rational points. Completeness must supply boundaries of rational sets. We will exhibit one non-empty bounded set of rationals with no rational least upper bound. Exact fractions finally meet an exact defect. Let F be an ordered field. We call F complete when it has the least upper bound property. Start with any non-empty subset A of F that is bounded above by some element U of F. Completeness requires a supremum S that also belongs to F. The boundary is not allowed to live in an imaginary customer service department. Thus, every non-empty subset bounded above must possess a least upper bound inside the field itself. A supremum has two jobs. First, it must be an upper bound. Every element of A is at most S. Second, it must be the least upper bound. If U is any upper bound, then S is at most U. The supremum need not lie in the set A, but for completeness, it must lie in the ambient field F. Consider the set S of positive rational numbers Q whose square is strictly less than 2. The number 1 lies in S. And 7/5 also lies in S because 49/25 is less than 2. 3/2 does not lie in S because its square is 9/4, which exceeds 2. We are asking whether all these rational approximations possess a least rational upper boundary. The set is non-empty because 1 is positive, rational, and has square less than 2. The rational number 2 is an upper bound. Indeed, suppose Q in S were at least 2. Because Q is positive, squaring preserves order. So Q squared would be at least 4 and therefore greater than 2. That contradicts Q squared less than 2. Hence every Q in S is below 2. And S is bounded above in the rational numbers. Before attacking the supremum, we need one integer lemma. If n squared is even, then n is even. Prove the contrapositive. If n is odd, write n as 2k plus 1. Then n squared equals 4k times the quantity k plus 1, followed by 1 more. This is odd. Therefore an odd integer cannot have an even square, so an even square forces an even integer. Suppose a positive rational R satisfies R squared equals 2. Write R as A over B in lowest terms, with positive integers A and B. Clearing denominators gives A squared equals 2B squared. Thus A squared is even. So the parity lemma makes A even. Write A as 2k. Substitution gives B squared equals 2k squared, so B is also even. Then 2 divides both A and B, contradicting that the fraction was in lowest terms. Hence no positive rational has square 2. Calling the missing value square root of 2 does not quietly make it rational. Assume for contradiction that S has a supremum R inside the rational numbers. Because 1 lies in S and R is an upper bound, 1 is at most R. Because 2 is an upper bound and R is the least upper bound. R is at most 2. In particular, R is positive. By trichotomy, R squared is less than 2, equal to 2, or greater than 2. Mathematics decline to offer a fourth mood. Define T of R as 2 times the quantity R plus 1, divided by the quantity R plus 2. Direct algebra gives T of R minus R equal to 2 minus R squared, divided by R plus 2. It also gives 2 minus T of R squared equal to twice 2 minus R squared, divided by the square of the entire quantity R plus 2. Since R plus 2 is positive, both signs follow 2 minus R squared. The formula looks engineered because useful formulas often are. First, suppose R squared is less than 2, so 2 minus R squared is positive. The first identity makes T of r larger than r, while the second makes T of r squared less than 2. Also T of r is larger than the positive number r. So T of r is positive and rational. Therefore T of r belongs to S. But r was supposed to be an upper bound of S. And we just found an element of S larger than r. Contradiction. Next, suppose r squared equals 2. But r is a positive rational. And the lowest terms parity argument proved that no such rational exists. So equality is impossible. A missing number cannot become a rational supremum merely because the proof would enjoy the convenience. Finally, suppose r squared is greater than 2, so 2 minus r squared is negative. The identities now make T of r smaller than r and its square greater than 2. The displayed fraction also makes T of r positive. We claim T of r is still an upper bound of S. Take any q in S and suppose q were at least T of r. Both numbers are positive, so squaring would give q squared at least T of r squared, which is greater than 2. That contradicts q in S. Thus every q in S is below T of r, making T of r an upper bound strictly smaller than r. This contradicts the leastness of r. The final case has now failed with the same efficiency as the first two. We constructed a non-empty subset S of the rational numbers and proved that it is bounded above in the rational numbers. Assuming a rational supremum forced 3 cases for its square. And every case produced a contradiction. Therefore S has no supremum in the rational numbers. The least upper bound property fails. So the rational ordered field is not complete. The rational numbers already support exact arithmetic, order, density, and the Archimedean property. Analysis also studies limits, cuts, and optimal bounds. These become unreliable when the number system can omit their boundary values. Our set contains rational numbers whose squares move ever closer to 2. Yet no rational number occupies the required least upper boundary. The purpose of constructing the real numbers is to fill these analytical gaps while preserving the arithmetic and order we already earned. Completeness means every non-empty set bounded above has a supremum inside the ambient ordered field. The positive rationals with square below 2 form a non-empty bounded set. But no rational can be their supremum. A candidate below the boundary is not an upper bound. One above it is not least. Equality requires an impossible rational square. Thus the rationals are dense and algebraically excellent, but analytically incomplete. Real analysis needs a completed number system.